All right, so we're doing day 5 of thermochemistry unit. We're going to talk about heating curves. And this is basically the same calculations that we've been doing, but it's going to require many of them for one problem. And you're going to be looking at a graph at the same time, so it tends to be a little intimidating for the past students, but it's actually, you already know the calculations. You're just needing to practice where to grab information from. And we're going to use heating curves to calculate this. So basically a heating curve I'm sorry, we're not there yet. So we're going to explain what occurs on each point of the heating curve, which I'll show you in some pictures in a minute. And we're going to be able to calculate the total energy for water to go through phase changes. And we can do this with not just water, we can do this with any element that goes through phase changes. For example, solid, liquid, and gas are phase changes. So we're going to be able to calculate the total energy that it'll take to go from a solid to a gas. So for example, ice to liquid to gas. That's what we're going to do today. We're going to calculate that with water. So basically a heating curve is just a graph of that. It's just temperature on the left side and time on the bottom. And it's just going to show you that as you heat up water, it's going to get hotter, obviously, but there are certain spots where it's going to be kind of like plateaued, and that's when it's undergoing the phase change. For example, melting ice or boiling water, the temperature actually stays constant. Some misconceptions are that as the water starts to boil and then gets to rapidly boiling, that the temperature is still increasing, but the temperature is actually staying the same. So we're going to talk about that's called an enthalpy change. So how much the heat changes or energy changes during each phase change. So when a solid substance is heated, for example, ice or even metals or whatever, any element on the periodic, when it's heated, the temperature will increase until it reaches its melting point. So the best example is ice, because not often do kids just heat metal until it melts. So that's why I keep using ice, because this is something you guys can see in your life, that you have seen in your life many times. So that's why I use ice and water as a reference point. But basically, your solid substance will be heated until it reaches its melting point. For example, ice will stay ice until it's heated enough for it to start melting, and that's the melting point, the temperature where it will start to melt and become non-solid. And then the temperature will stay constant during that melting process. So you can heat up an ice cube and it's going to get up to a certain temperature, but then it's going to plateau. It's going to go straight. It won't get any hotter until it's completely done melting. So that's something that's pretty cool when we're doing phase changes in these substances. So when a substance is completely melted, you can also keep heating it up and it will boil. Okay, we can see this in water as well. Once you melt ice, if you keep heating it, it will get hotter until it starts to boil, and then that's the boiling point, and that temperature also stays constant during that boiling period until it becomes a vapor. And then once it becomes a vapor, then it will start to increase again. So there are two types of calculations that we are going to do. We're going to use the change in heat calculation, and we're going to talk about we're going to do the dimensional analysis. So you'll see, once we see the heating curve, you'll understand what I'm saying. But here we use this equation when we're looking at the curve going up. When we see like a straight line, when the stuff is getting heated. Okay, when temperature is rising, we use this equation. And when the temperature is being plateaued, or I guess here flatlined, okay, you're going to use dimensional analysis to find the heat. So there are also two new, I wouldn't say vocabulary words because they're not just one word, but vocabulary phrases that you should know for the test. And basically, molar heat of fusion, all that means is the amount of energy to melt something. So molar heat of fusion would be how much energy you need to melt a piece of ice. So don't get too confused over some of these words. It just means how much energy needed to melt something, and this same thing, how much energy needed to boil or vaporize something. So make sure you have these two words straight before the test. You'll need to know them for the calculations anyways. All right, so here's what one of these problems will look like. This is the heating curve, okay? You have a temperature here and time, so a temperature versus time graph, and the lowest temperature will be down here. And then, so let's say we're starting to heat up a piece of ice, okay? So the ice is this temperature, and we start to heat it up. And basically the whole goal of this, if you'll read this, what is the total amount of heat in joules that must be added to this much ice for it to turn to steam, okay? So what our whole goal is, we're going to add heat, until it reaches our goal of steam at 103 Celsius. And what we're doing is we're just going to find the joules here, we're going to find joules here, joules here, joules here, joules here, and we're going to just add them all up. So this is a pretty involved math problem, but all of the problems are pretty simple. It's just there's multiple steps. So we're going to find out how much heat it took to melt the ice from here to here, or for ice to start melting from here to here, okay? And then we're going to calculate how much energy it needed to melt, okay? And then we'll use dimensional analysis here, and then this equation here, okay? So the blue parts, we use the heat equation, or specific heat equation, and then for the green parts, we use dimensional analysis. So we're looking at 5 math problems for this one calculation. We're gonna calculate the change in heat here, here, and here, given stuff that they are going to, like right here. You'll be given this. So you'll be given the question in here and this chart right here, okay? And what we're going to do is find out how much heat did it take to get the ice to melting point, okay? And how much heat did it take to get for the ice to completely melt? And we just basically calculate each step of the heating curve, and then we're going to add it all together. So here's the same question. Okay, so basically this is what you'll be given on the test, okay? And then you have to calculate everything. So basically we're just going to find the heat for here, specific heat for here, and use dimensional analysis here. And then we're just going to add it all together, and that's our final answer. So for the first section of this heating curve, okay, this whole thing right here, that's the heating curve. That's what we call a heating curve. It's not, every substance doesn't look exactly like this, like every substance doesn't boil at 100 Celsius and whatever, but every substance has this heating curve where solid to starting to melt, and then it melts and it stays constant. And then from the liquid to the gas, you heat it up till it starts to vaporize, and then that's constant until it's all vaporized, and then you can heat it up again. So every substance has this heating curve like this. Obviously the temperature will change. It's going to require more energy to heat certain metals than it does for water, or to vaporize metals than it does for water, and so on. So all right, so let's do this first part of the heating curve, and this is where we use the specific heat equation. Okay, we're warming up ice so it starts to melt. So remember, Q equals mass. Okay, so mass is given to us in the problem somewhere right here. Okay, so that's where the 165 comes from. The specific heat is given to us here. Specific heat of ice is different than specific heat of liquid water. So that gave the specific heat of ice is here, and we got it from right here. Okay, and then the change in temperature. Basically, the change in temperature is the final temperature minus initial. So it'd be 0 minus -5, which is 5 degrees Celsius. So then you just plug all that in your calculator and you get this answer. So that's easy. And we're going to do that here and here as well. Now this one, we're going to use dimensional analysis to find the heat. Oh, also the mass, that's where you look at for your significant figures. Don't look here or here. These are going to be considered infinite significant figures, so use your mass for the significant figures. Okay, So number 2, we're going to use dimensional analysis to find the joules, okay? Because we don't have a change in temperature. We don't have, we're not going to use this equation. We're going to use dimensional analysis. And what we have is we have the mass, okay, of H2O, okay? And we need to get to joules. So to get to joules, we must convert to moles. Because for the heat of fusion, okay, that's to melt something, it takes this much joules per mole. So if we can convert this mass to moles, then we can convert to joules. All right, so this right here, whatever is up here must go at the bottom. So that's where you have your grams of H2O down here, and we're converting to moles. So oxygen weighs 16 plus 2 hydrogens, and that's about 18. All right, so our grams canceled and we now have moles. So we can convert moles to joules using this right here, this thing that the question gave us. So it takes 6.01 kilojoules per mole. Energy, here we go. So the moles cancel, and then you will put your, we will convert to kilojoules. So our moles cancel and we have kilojoules. However, we need our answer in joules. So we know how to convert joules, kilojoules to joules. It's just 1,000 joules for every kilojoule. Okay, and whatever, we just plug that into our calculator and the answer will be this. So we're basically doing the same thing for every step. This would be the QMC delta T equation, and then this would be the dimensional analysis equation. So we're going to do our next step, and here, since it's since it's heating up, we can use our Q equals MC delta T equation, the specific heat equation, okay? So for the liquid, the mass, we are going to use the same number, okay? And the specific heat of the liquid is 4.18 joules. This is something we've known since a couple of lessons ago, okay? This is something you kind of have to memorize. And then here, 100 degrees Celsius. So basically, if you look at the temperature change, all right, you have, it's going from 0 to 100, so it's not that much of a math problem, but so yeah, you have 100 degrees temperature change. And then you just plug in your calculator and you have your answer. All right, so now we're going to do the fourth section of the heating curve, which this is dimensional analysis again. So we're going to use the same, basically the same everything except the delta H, the heat of vaporization, okay, that's going to be a different number. So we start out with the same mass, and then we need to convert it to moles like we did here. And then the mass will cancel and we have moles. Now, this number we took from vaporization because this right here is actually the boiling, the water is boiling. So this right here, the water was melting, okay? So we had to use the delta H of fusion, okay? Change of heat, fusion. And here we're having to use vaporization because it's boiling. So the moles canceled and now we have kilojoules, but again, we aren't looking for kilojoules because it says heat in joules, okay? So we just have to convert that to kilojoules, and that's 1,000 joules is for every kilojoule, just like 1,000 grams is in every, every kilogram. So that's just stuff you guys should have known since middle school. And then we plug it all in and we get this. So now we have one more equation, and you can tell because of the diagonal line, it's actually the temperature is increasing or it's changing. So we're going to use the specific heat calculation, the Q equals MC delta T, and same mass, not same, but we're going to grab the C from up here, right there for the steam, okay? And then here, we're going to take from the change in temperature. And if you'll notice, it says 3 degrees Celsius. So the 3 degrees Celsius comes from here. So basically, we know that this was 100 degrees, and then 103, we're changing it, and we need to stop at 103. So it was at 100, and then we stop at 103, so we just take the difference of that, if you're wondering where the 3 came from. All right, and then we plug it into the calculator and we have our answer. Now, we have every piece. We know how much heat it took to get from here to here. We know how much heat it took to get from here to here. We know how much heat it took to get from here to here, and same and same. Now we just add it all up and we have our total amount of heat in joules. Okay, so once you plug that all into the calculator, you will have this many joules, and that is your final answer. Let's do basically all of your homework together. I only give you one problem on your homework, but it's all of this. So let's go ahead and just do it, and that way you'll know exactly what's expected on the test. So we're doing a heating curve. So basically this thing right here is the heating curve. So anytime you heat up an element as something solid, it's going to heat up for a little bit until it starts to melt. Once it starts to melt, it stays at a constant temperature until the melting is done. Then it will heat up again, and keep in mind you're constantly adding heat. Even though you're adding heat, so here you're still adding heat. So basically, let's say you put ice in a pan and you're heating it up on the stovetop. You're still adding heat. That stovetop is still heated and applying heat to the pan, but the ice will not change temperature from starting to melt to completed melting. So even though you're adding heat, it's still not. It's just not increasing the system's temperature. So that's why you still calculate the heat added. The temperature does not change during this point. Which I think is pretty cool. And then here, this is once the liquid is once it is melted, the liquid can be heated. Well, it's still being heated, but then the temperature will rise here, okay? And then once the temperature rises to the point of boiling or to the point of vaporization, again, it has this plateau, and I think that's super cool because it doesn't like. You're still adding heat. Let's say you're still adding heat to your water that you're trying to boil. Okay, you just barely see the bubbles here, and then here it's a rapid boil. From that to that, it doesn't increase in temperature. The system doesn't. So if you had a thermometer, and we'll probably do this in class, where you have the first little bubble starting to form in the boiling or point of vaporization all the way to actual rapidly boiling and vaporized, it doesn't change temperature. It's the same temperature. So, and then once it's gas or vaporized, you can cause it to heat up again. So let's take a look at the problem, and we're actually doing water again. So it's not going to be identical because you have a different amount of water. The ice temperature prior to it starting to melt is different. So we're going to have different numbers to plug in. However, the process is the same as the lecture that we started, or the lesson that we did just prior to me recording this video. So it says 72.3 grams of ice. So that's our starting point. Okay, this is how many grams of ice we have, and it's at negative 15 degrees Celsius. So here is negative 15 degrees Celsius. And then it says has heat energy added to it until it becomes steam at 145 degrees Celsius. So at the hottest point, it's going to be 145 degrees Celsius. And then since it's water, we know that it'll start to boil at, there's words here, so I'm going to write it kind of right here. 100 degrees Celsius, it starts to vaporize, and then here, once it melts, it's going to be at 0 degrees Celsius. So we have our points on the heating curve. It's asking for the total amount of heat energy needed in joules to accomplish this. So basically we have a calculation here, and remember, anytime we have these rising temperatures, we're going to use that Q equals MC delta T equation, the specific heat equation, okay? And anytime there's plateaus, since there's no change in temperature, we can't use this equation. We use dimensional analysis here and here, okay? And that's where we change from the mass that we have to moles to kilojoules, and then of course kilojoules we'll have to convert to joules because that's what the question's asking somewhere here. Okay, so this is a multi-step problem. They will take a very long time. They will be worth a ton on your test. So make sure you know how to do these. Make sure you know how to do every step. Once you do a couple, it's like, okay, I got this. It's literally just this equation and dimensional analysis just 5 times, and I'm done, and I add. So it's just knowing where to grab your information, to me, is the most difficult part. And remember the, what is this? The specific heat of water, okay? That's one thing you'll need to know. It's 4.184, okay? Same units here. And so anyways, let's get started. So calculate the energy required to heat the ice to its melting point. So basically A is this right here. We're doing this for A, okay? So we are on that slope, so we're going to use the Q equals MC delta T equation. So, mass we grab from the problem, right? Oops, you can't see that. We grab from the problem. So it will be 72.3. The specific heat of ice is 2.01. Okay, and then we have the change in temperature. So the change in temperature, with water, it's super easy because, I mean, from 0 to 15, it's a 15-degree difference. Okay. So you just plug that into your calculator and you'll have your answer. So 72.3 times 2.01 times 15, 2,179. Okay, so as far as what's it called, significant figures, I told you in the lesson, you use your mass, okay? So we have 3 significant figures, so we need to really stop at 2180, okay? And that's in joules. Okay, so we have our first answer. All right, so the next one, energy required to melt the ice. So melting the ice, so this is where it starts to melt. This is where it is completely melted. So this is, it's a plateau. We're using the dimensional analysis because we don't have a change in temperature, so this equation is not going to work. So the energy required, so we always start with our mass, okay? Our mass here, 72.3. And that's grams of H2O, okay? So we need to convert that to moles, and to convert H2O mass to moles, we just need to find out how much H2O weighs. So oxygen on the periodic table weighs 16. Let me find my periodic table. Here it is. So oxygen weighs about 16, and hydrogen weighs about 1. Once you add 2 hydrogens and an oxygen, it's going to weigh around 18. I'm not going to make you watch me type it in the calculator, but it's 18.0, is it 001? Yeah, 002 grams per 1 mole. Okay. All right, so we have converted it to moles. The grams cancel. But we don't want moles, right? We want joules, but we don't know how many joules are equal to 1 mole of water. Heat of fusion, remember, means melting, and that's what we're working on. We do know that how many kilojoules, so 6.01 kilojoules, oops, 6.01 kilojoules, okay, for 1 mole of water. Again, I just took it from up here. The moles of water cancel, and we're at least in joules. Sorry, they're doing construction. Okay, so now we just need to convert kilojoules to joules, which is easy. So for every 1 kilojoule, just like kilogram is 1,000 grams, there are 1,000 joules. So now we just take our calculator, divided by 18.002 times 6.01 times 1,000. All right, so we want to use the mass again for our significant figures. So we just need 3. So we have 1, 2, 3. So okay, that's plenty. So we need 3 significant figures, so we need to cut it off here. So the answer would be 24,100 joules. Okay. All right, let's do the next one. The next one is a slope. Okay, so we're going to use this equation because we actually have a change in temperature. So we're going to use that Q equals mc delta T. So Q, mass always is the same. It's whatever the problem gives you. Change in specific heat, we're going from, oh, this is the water, okay, so it's water to starting to vaporize. So here we know it's 4.184. And then change in temperature. So change in temperature is 0 to 100. So the temperature change is 100. That's easy. Let me just calculate it. Put it in the calculator. And that's our answer. These are easy. So 72.3 times 4.184 times 100. 3 significant, well, let's just, 3 significant figures. So 1, 2, 3. So we're going to write 30,300 joules. Okay, I know this video is long, but I'm literally doing all your homework for you, so I guess you don't have to watch this part unless you're confused. So calculate the energy required to vaporize the water. So here, it's a plateau, so we need to use dimensional analysis. So basically it's the same thing here, except the energy will be, the energy required to vaporize is different than the energy required to melt. So vaporize, the energy is this much. So basically it's the same dimensional analysis, but 40.7 kilojoules per mole is what we'll be using there. So mass is the same. We need to convert to moles. And then from moles, we convert to our energy or heat, which is 40.7 kilojoules, which is what we grabbed from up here. Okay. Moles cancel. And we have kilojoules, which is okay. We just need it in joules. So we're just doing this conversion, then we're done. So we're going to take our calculator and just type it all in. 72.3, oops, not divided, not time, oh my gosh. Divided by 18.002 times 40.7 times 1,000. All right, so we have 3 significant figures, so 1, 2, 3. So 4 won't round the 3 up, so it's 163,000 joules. Okay, and calculate the energy required to heat the steam to 145 degrees Celsius. So heat the steam, so that's this part. We're using the specific heat equation, and we will be using the specific heat of steam, which is 2.02. Okay, so Q equals mass times specific heat of steam times the change in temperature. So from steam to 145, so steam is at 100 degrees Celsius. Okay, so from here to here is 140, it's actually 45 degrees Celsius. Okay, and then we just take that and multiply it. And we need 3 significant figures, 1, 2, 3, so 657. joules. Okay, so the total heat needed to get from negative 15 to 145 for water, we basically add all of these up, and that'll be our answer. So 2180 plus 100 plus 300 plus 163 plus 6570. So our final answer would be 150. Okay. That's it. That's how you do these problems. Just a bunch of steps, okay? But I mean, each one was easy, and then you just add. So nothing like new or crazy. It's just a bunch of steps.